Hello and welcome to a presentation which deals with the forecasting of international air passenger demand using time series Sarima modeling on a seasonal dataset, which demonstrates how this would be used for future forecasts for the next 10 months. This was made in collaboration with my teammates Bilal Qureshi and Mohammad Bilal Azeem. So our project is focused on modeling and forecasting air passenger demand using a well-known data series that we got from Kaggle called the Air Passenger Demand Dataset. And this basically shows the information from the year 1949 to the year 1960, giving a total of 144 observations measured in thousands for the number of passengers for each month. So we all know transportation is in demand and a serious worldwide issue. So this information can be used to make better understandings on the trend and seasonality of this data, which can also be used to help air transport industries in better scheduling, staffing, as well as marketing of their flights. So our main research goal that we set here is, can we model and accurately forecast monthly air passenger volumes to support planning in the airline industry? So from the analysis of the time series plot over here, we can make the following observations. We can see that from the plot, there's a clear upward trend in the passenger numbers. This indicates a steady increase in the air travel over time, likely due to population growth. We can also observe clear and consistent seasonal patterns, peaks annually, particularly around mid-year. This kind of pattern suggests that people like to travel during certain months, probably around summer holidays. It also means that this could be the time where the prices are the cheapest. Talking about the variance, which we can see increases as time progresses, indicates a non-consistent variance, which is one of the reasons we would be applying a box-Cox transformation later to make the data normal. So talking about the behavior, we can see that as a trend rises, the seasonal peaks become more pronounced. That's one of the key observations from the behavior. And talking about change points, while I don't think there are any certain change points, we can say that from the year 1955, the demand for air travel rapidly grows. We performed a visual analysis, and from the scattered plot over here, we can see that there is a strong upward trend from the previous month's data and the current month's data, which also indicates that there is a high autocorrelation between the data points, which also means that there is a non-stationarity in the data. When we observe the ACF plot, we can see that there is a slow decaying pattern over many lags. This is also a sign of non-stationarity in the data, which means that the variance is not constant over time. This confirms the need for differentiation before we can fit any of the Sarima models. On seeing the PACF plot, we can see a significant spike at lag number 1, which then cuts off, suggesting a presence of an autoregressive 1 process, which can be then used as the AR component for the model during our model specification stage. So when we observe the QQ plot and from the results from the Shapiro-Wilk test and the ADF test, we can also see that most of the data points follow a straight line, which indicates that most of the data is normally distributed apart from the tail ends, which seem to be tailing off, suggesting that the data is still not normally distributed and we would need differentiation to normalize the data. A Box-Cox transformation was then applied to stabilize the variance and improve the normalcy of the time series data. A suitable lambda of -0.295 was chosen, and from the visual analysis of the plot, we can clearly see that the transformation is compressed to the scale, especially during the later years where the variance was, in the previous case, rapidly increasing, which confirms that the variance is now constant. From the ACF plot of the transform data, we can also see that there is still a persistence of a slow decay, which still suggests that the series is non-stationary in terms of its autocorrelation structure. So we would still need to process with differencing. If we observe the QQ plot, we can see that the linear alignment of the data points is better, however, still deviates at the tails, which further emphasizes the need for differencing. And the new Shapiro test results also shows that it now has an improved W value closer to 1 and a P value which is still lesser than 0.05, although improved from the previous P value. For the model specification, since the series exhibited a clear evidence of seasonality, we explored the Sarima modeling. And as mentioned before, we had to apply first order differencing as well as seasonal differencing to remove the stationarity and seasonality in the data. This helped us in stabilizing the variance of the data. From the ACF plot, we can get a Q value of 1, as well as, since there is a lag at spike at lag number 12, we can also infer that the seasonal Q is also 1. The PACF plot shows that there's a spike at lag number 1 which then drops to 0, suggesting that the P value could be 1, as well as the seasonal P also could be 1. We would now be proceeding with gathering more models from the AIC-BIC table, as well as fitting these models using techniques like CSS and ML, as well as forecasting the next 10 months data.